So welcome back to the second session. So where I left at a position where you had the loss and you want to basically find out the risk and then proceed. I'll come to the actual optimization problem once these sets of slides are over. And you can solve, I'll give the algorithms for the stochastic or reliability optimization. So anyway, so you want to find out the risk, and risk is basically the expected of the loss. Loss means whatever underestimation, overestimation problem you have. It can be the trying to minimize the variance, or you want to maximize the negative of the expected value, or take the ratio of maximize the ratio of the returns to the risk, or minimize the ratio of the risk to the return. So there can be different combinations of that. Or else you can take the odd moments as to be positive, even moments to be negative, skewness, kurtosis, those all can be included in different types of problems. So you take the expected value of the loss, and in this case the loss considering the Linex loss. So obviously for different type of loss you will have different values of expected loss, the risk. So which I drew on the or written on the board was basically the loss corresponding to the expected loss corresponding to the squared error loss function. It can be for the Linex loss function, it can be for the Lin loss function, and all these things can be incorporated. So I'll just give one example. So the bounded risk, the risk value would be given. So the risk is this. So obviously sigma square is unknown. So if you bound the risk, that means you have capacity constraints, financial constraints, manpower constraints, budgetary constraints, anything can be correspondingly formulated as a risk, bounded risk problem, where lesser the value of W is, more number of N's you can take, which means the budget is increasing. Is basically the inverse relationship. So a different type of other formulations can be done, but I am taking the simplest one. So once you have the bounded risk, you want to find out N. So now obviously theoretically the value of W as it tends to 0, it will give you some ratios here. So and that ratio as W tends to 0 in the limiting case, the value would give you the actual theoretical number of samples, observations, which you will take in order to basically find out the best possible estimate. Your main task is to find out the estimate based on the sample observations, because that will minimize your overall loss. That is your target. You want to minimize your loss, because in all the optimization problems, basically what is the main task? You take the expected value of the utility function or the variance of the utility function, try to maximize the expected value of the utility or try to minimize the variance of the utility. So this is a utility is a function, which is the value function which you have. This is also a type of utility function which you consider. So once you have the value of as W, which is not the weights, again I am mentioning, which is the overall risk, as you minimize you get the, theoretically you should get the value of N, which is basically given as D. Now the problem is that if you want to minimize that, technically either you use stochastic programming, which I will come tomorrow, or else you use a different type of technique which is known as sequential analysis. Sequential analysis is in the sequential optimization programs. These are generally used where you basically have a stopping criteria. Based on this you want to find out or estimate your function. So in this case your actual value of decision variable is N. So this is basically the stopping criteria which we can formulate in a very simple sense. It can be made more complicated depending on what different type of loss functions which you have. I am only taking one loss function. One loss function in the sense that in this balanced loss function I am only considering only one part with W as 1, and I am considering the Linex loss and trying to basically estimate the value of mu which is basically using x bar n for the normal distribution. Now there are many methods, and I'll basically discuss the sequential sampling method. So there are Bayesian methods also. I'll just go through the simple norm. Now just for your interest to mention, this value of n which you want to find out, this is stochastic or non-deterministic, because each time you take w, each time you take the sample size, so obviously this sigma square will be replaced by the best estimate from the sample, because sigma square is unknown. So you pick up a sample of size small n, estimate the value of sigma square, replace that, and then proceed. So each time when you're picking up the sample, the sigma square hat is changing. So if it is changing, then obviously this is non-deterministic, it will have a distribution. So this distribution generally is known as the Wald's distribution, WALD, Wald's distribution. And consider this very simply like this: if you take, to give an example, if you take some material and throw it from a height, it falls and breaks. So the number of pieces to which it breaks can be 0, that it doesn't break, or it can be infinite in number. So that distribution basically gives you some information about what type of distribution for n you will have. N can be technically from 0 to infinity. So we want to basically find that, based on which we want to actually optimize and find the estimate. Our main task is not to find the value of n. Our main task is basically to estimate or forecast the parameter for the population, which in our case is mu being estimated by mu hat. Now this mu hat would change depending on what type of loss function which you have. So there are, these slides I would not discuss in detail, I'll just give the overall picture for the 4 slides coming. Now in sequential analysis, the procedure happens like this. So sequential analysis can be either from the statistics point of view, or can be from the optimization point of view. Your main task is to take initially a sample size, arbitrarily any sample size, and then proceed step by step. So those steps are decided by the stopping criteria. So what is the stopping criteria? Is this one, where you should stop. The moment n is greater than this, you will basically stop. So what you do is that you pick up a sample size of small m, can be 10, 12, 13, whatever. So once you have that small sample size of m, you immediately take at those set of observation x1 to xm. From them find out the best estimate of sigma square m, which will be the standard error square for the sample. So the A would be given, you take some value of w, replace sigma square by sm square, find out and check whether that value is less than m or greater than m. It's not n, it's m as is mangoes. If it is true, then you stop. If it is not true, you proceed. Now the steps you proceed can be of different varieties, or different colors, or different types. So in one case you can proceed one step at a time. That means you take m, verify the stopping criteria. If it meets, stop. If it doesn't meet, you take extra one observation. Now it is m plus 1. You check again, this now becomes s square suffix m plus 1. Put that in this equation, verify with m plus 1. If it agrees, stop or proceed to the next step. So the next step is again now m plus 2. You proceed in this way and then take a decision and stop. Where do you stop? You report that value as now capital N, because this is random. And this type of procedures are very heavily used in marketing, where you have to make a decision based on what is your stopping criteria for the marketing survey which you are going to do, because your amount of money is limited and you want to optimize. So you take that capital N in such a way that you can basically decide how you are going to proportion your money in different zones or different sectors, like in western zone, eastern zone, northern zone, or regions, based on which you can do your marketing survey. So one criteria would be taking one step at a time. That means you are in block 1, proceed to block 2, block 3, block 4. The first one is M number of observation. Second set of observations is like this. You only proceed in blocks of 3. Now you take M number of observations, check this criteria. If it is met, stop. If it doesn't meet, you take M plus 3. And you go to M plus 6, M plus 9, and proceed in this way. Now there are varieties of such plans based on which you can take the observations or decide on the decision variables. Now your decision to basically find out which is the best rule basically depends on two important things. Number one, what is the total cost, and what is the total number of basically samples you are observing. Now the question is that why it is important, because each time we go to the market we have to take an observation, which means it entails a cost from our side. So I would rather go into the market, take observation 3 at a time, or I take one observation at a time. That is the decision criteria which you have to do. Now what is the flip side of that? If I go to the market once and I take 3 observations or 4 observations or whatever it is, it entails cost. But on the other hand also, it entails an overfitting or an underfitting. So if I actually consider the number of observation which I want to take is 10 in number, and if I reach the 9th one and then I jump and take another 3 which means I go to the 12th one, so that means I am overfitting. That means I am trying to basically take more observation, which is more costly for me, in order to estimate whatever my total cost is. Now this compromise, whether you want to basically overfit and find or basically reduce the cost or increase the cost and do a precision estimation, would basically depend on what type of examples you are doing. So this basically comes as a sort of quadratic programming, where you have the variances, the cost, so on and so forth, and based on that you take the decision. So the next 4 slides are basically this idea which I stated, that there are different types of stopping criteria based on which you proceed. So this comes under the umbrella of say for example sequential sampling or multi-stage sampling, which is used in marketing, used in finance, used in a different type of locational facility location you want to build, because whether you want to build the facility or not build the facility would depend on the total cost. So you have to basically make a decision. So that decision would depend what is the overall cost you are basically going to entail for yourself, what is the total number of factories or machines you are going to buy, what is the total number of workers you are going to employ, so on and so forth. So there is basically a whole gamut of cost structure which is there. So some of the rules, I'll just mention the rules. These are just simple algorithms. If you read it, you will understand. They are nothing to do to programming. You just go step by step. Decide one, if not, you proceed to the next step. Only important thing is that you have to decide, depending on what your problem is on the stopping criteria, and that would depend on the loss function which we have.
Yeah, we are considering what that means we are want to minimize risk towards.
Yes, we want to make risk as low as possible, such that we have to spend a whole amount of money to take a lot of observations or samples, such that we make the difference between the estimate and the actual parameter as low as possible. So that
some cases we don't get, because if I see the expression, why we are not directly writing W if I put W equal to 0, you will get some n.
Yes, you will get that n value. That's no problem. You can get the n value, but there I have made a compromise. W value putting at n, you have some costs. So what if I slowly increase the cost? So the n number will increase. So my efficiency will be much better. So I want to make a compromise between what is my efficiency and what is my cost. So actually your cost function generally should be consisting of 2 times. One is if I cost number of observations which I considered, if it is n, so per unit cost for taking one observation is C, so it will be C into n plus the expected loss which I have also to be added up. So this is decreasing, this is increasing. So you have to make a compromise, because as you increase the number of observations, the variance in decreases. As you increase the number of observations, the total cost for marketing or total cost of observations increases. So you make a decision where you find out the best possible combination which it is. And remember, this is not a linear function. And this may not be a linear function also. Like say for example, you are ordering goods and you are getting discounts. So in the first 100 you pay a cost, say for example, of 100 rupees per unit. Then you order, say for example, 101 to 200, the cost decreases. So obviously it's not a linear function, it's a non-linear function. So you have to basically make a compromise between them. Now the rules which are there are, if you read it, they are just stepwise algorithms. This is nothing complicated here. You must just make a decision, stopping criteria, how many number of observations you are going to take, and you can basically make your problems accordingly. So few, I'll just mention the names. So one is the two-stage sampling, where you go in steps of take two jumps, not two observations, two jumps to reach your stopping criteria. Now what is actually required is like this. If you are taking observations, either you can overshoot the value of D, which is the actual observation, or be less than that. So what your main criteria is, you should be as close as possible to D. So that means you are trying to basically minimize the dispersion which is happening plus D and minus D. So that you can also model it if you want to basically bring that variance for expected loss, which is the risk, the total cost, and the overshooting or undershooting, you can basically plan it accordingly. So obviously that would become a multi-objective problem. So if you want to keep it single, you keep one of those problems as linear, non-linear, and solve it accordingly. In the purely sequential sampling, I am just reading the highlighted points. You will take one observation at a time, as I mentioned, and then decide when to begin, when to stop. In the 3-stage, you go in jumps. That means it's like this. 3 stages can be of two flavors. Like you are traveling in a car and your destination is going to come. So what you can do is that there are two methods. Either you can start accelerating your car from the source, and as you slowly reach, you slowly put on the brakes and decelerate. That's one policy. Another policy can be basically you start slowly and then accelerate, so that as you approach your destination. So in this cases, it is seen that if you basically start in a slow mode and then accelerate, the probability of overshooting is higher. And basically if you start on the reverse mode, the probability of undershooting is higher. So you basically make a compromise. How now you may ask the question why it is important. Say for example, it is some sort of destructive testing, and you take an object, test it, so obviously you lose that product. So and if it is huge amount of cost on your part, you make a decision whether you want to take one extra observation or not taken one extra observation, to make the decision whether the quality parameters are met or the estimation of the lifetime of a product, whatever it is, right or wrong. So 3 stages is basically like this, where you accelerate and decelerate, or vice versa. And these are the stopping criteria you estimate and then reach your main criteria. So your main aim is to estimate D using capital N. So in the long run, you are also trying to find out the expected value of N, and then take a decision that how close or far it is from D. And in the batch sequential sampling, you go in batches. Like you take 3 observations at a time for some set, then you take 5 observations at a time for some set, and then make a So these what sets you should take are basically dynamic. That means you can employ different type of sampling rules to find out what is the best criteria where you want to stop. So this is the batch sequential which I have mentioned. and this is just the algorithm written bullet point wise. Now I'll solve a multiple linear regression model using this method. So this was the background. So what is written on the board is that you have a multiple linear, very simple multiple linear regression. It can be made depending on what type of problems. It can be, for different problems it can be solved accordingly. It can be done for forecasting also, time series also, whatever. Now you have, and these are written in matrix notation. So is y is equal to b naught plus beta 1 x1 plus beta 2 x2, so on and so forth. And let me consider very simply, for the time being, the errors are normally distributed with 0 mean and sigma square as error. So it can be otherwise also, but I take the simplest one. Now if you were doing the regression part, you would have basically solved it using the simple multiple linear regression. I am not going to do that, because for me beta estimation and y estimation both are important. So this is where I slowly bring different type of loss function or different type of optimization. Now our main aim for the problem is, I'll give you the overall picture. We want to have two different models for two different estimates. So that means 2 into 2, 4. And I'll compare the models, give the results. So what is good and what is bad is relative depending on the situation which you are using. Now in the first, if you remember, in this loss function which we had, I'll go back to the balance loss function. So what we are doing is like this. In the goodness of fit and precision of estimation, we interchange the losses. In the first case, we take the goodness of fit as ordinary least square and the precision of estimation as Linux loss. And in the other case, we swap the errors. Now under them there are under two rules. This I am just giving as 4 cases to be studied. The other rule is that I am using different type of estimates. Now if you remember, I mentioned that x bar n is the best estimate for the mean of a normal distribution under the ordinary least square. So there would be different type of estimates under different loss functions. So I'll try to take 2 of them and try to do the experiment. So you can use different types of loss functions, different type of estimates in order to estimate. So the question would be, the estimate xn bar is the best estimate considering the unbiasedness and consistency if I consider ordinary least square. It may not be the best estimate under other circumstances. Like if I use the Linux loss, it may not be the best estimate. Or if I use the 0-1 loss function, it may not be the best estimate. So I'll take 2 loss functions and their corresponding best estimates and then try to proceed. If I change the loss function, my estimates would also change. I have to redo the whole set of calculations accordingly. So for our case, we are taking, as I mentioned, the best estimate of beta which I want to estimate. So it is a multiple linear regression, so I am using beta. And the 2 different models are as stated. It is we solve 2 different models. In the first case, goodness of fit is reflected using squared error loss, while the Linux loss function portrays the precision estimation, that is so-called model 1. In model 2, the precision estimation is SEL, that is reversed, while the goodness of fit is Linux. Now in the first case, I use for my comparison the best estimate for beta as the one which I find from the ordinary least square. And in the next case, I use the beta which is the best under the Linux loss function. So there are 2 varieties of betas. Obviously they will change. So I compare them under which case it is weight. Like this, basically I am trying to change from a Cartesian coordinate to a polar coordinate and vice versa, and trying to utilize 2 different type of estimates in both the cases. Now these are all available in literature everywhere, but I just state it without the proofs. under ordinary least square, the best estimate of theta is this, we all know. And under Linux laws, the best estimate, so hat remains the same, I am just using the suffixes to differentiate them, it becomes this. So now you see this ordinary least square is plus and minus a certain nuisance parameter or term. So if A is positive, this becomes negative, if A is negative, this becomes positive. That means you are trying to penalize that estimate either positive or negative depending on what the A value is. So our aim is, I am again repeating, use this for the case when goodness of fit and precision estimation is squared error Linux and vice versa. Again use this theta hat Linux under goodness of fit and precision estimation being squared error Linux and vice versa. So that's the idea. So I write the models without the proofs. I'll just give only one results. Again I'm saying that if somebody is interested, I can share. The reason that I am not going to do the MATLAB coding is that the results are known. If you want to use that, you can borrow it from me, because these were done either by me or by students, so they are in MATLAB, not in R, but you can easily convert them into R and use them for the forecasting problem, for the estimation problem, and all these things can be used, and you can bring different flavors in the problem. Now in the first problem, again I'll just state it without the details. So here it is. Don't be too much bothered about the details of the equation, just concentrate on the first part. So if you check starting this curved bracket from here to here, it is a squared error, check, because it is what? This transpose multiplied by its value, which is a squared error loss. And if you check the second part, it is a Linux loss. Second part means from the curly bracket till the end of the curly bracket. So I will put weights lambda and 1 minus lambda depending on what my actual weightages would be. And I use in this case the beta hat as to be the squared error loss. So obviously the squared error loss would be the best under the first instant, not under the second instant. You understand? Because that is what is the best estimate under the circumstances. So if I use beta hat or beta for the squared error loss, the estimate, under the Linux there would be some error. So I want to basically find out that error. Now if this is the first problem, our other favors of the problem, I will just mention that and then just state it. So in second case it would be the same model, but now I am replacing the beta hat with the Linux. So this is the estimate which I am replacing. In the third instant, I swap these errors. That means this Linux goes to the left part and the squared error comes to the right part. Then for that one, I used again the squared error and again the Linux loss. Now if you solve them, there are very similar set procedures to find out the risk. You find out the risk, bound the risk or optimize the risk, and then solve it. Now the solution which you get would basically be utilized for different situations. I will give the practical use of one problem and its results. So this was model 1. Model 2 is the same problem, again now you have Linux. Model 3 has swapped one where Linux goes to the left hand side and it comes to the right hand side, now the squared error loss. And for the model 4, again the third balanced loss function, but now the estimate is now the Linux. Now what type of problems we want to see? So generally we will do some simulations, but before that the background of the actual part. This data is decently, I will come to the data first, then I am come to the simulation studies. Yes. So this is the data. So this data came out in 1997 in a paper by Kelly and Barry in Statistics and Probability Letters, which basically deals with about 20,640 observations related to 9 variables. So what is the background of the study. So the study was to basically predict the mean household price in the state of California in the 1990s. So you want to predict the house price and what were the variables based on which you are trying to predict the house prices. So the house prices are, and the predictions are based on median income of the families, median income squares, median income cubes, median age of the houses, total number of residents which is there in that area in per house, total population in that zone, total number of bedrooms which are there in the houses. This you can find the link. I think I don't have it, but I'll give it to you. This is the total number of bedrooms. P is the population. Again, H is the household average numbers of people who are working, if I am not mistaken, because there would be people like kids are there too. If there are 2 kids and father and mother, husband and wife, so they are considering the number of people who are working. And obviously you would be interested to find out, okay, now this model is already given in this paper, so you need not check the normality of these variables. So technically this would be beta naught, beta 1 into x1, beta 2 into x2, beta 3 into x3, beta 4 into x4. x4 means the log of mean age of the house, beta 5 into x5, beta 6 into x6, beta 7 into x7, beta 8 into x8. And the error has the distribution of normal, zero mean and some variance. So it can be checked. So with 20,640 you can basically divide it into a set where you want to basically predict the beta hats and then basically try to test how good or bad your predictions are with respect to the general case of regression models which are used. Now how do I use the data? So this we did it purposefully for our case of studies is this, and what we want to study. So I give the background. So we apply for all these 4 models the different type of sampling techniques we had. Now what we did is that in order to basically ensure normality, you concatenate the overall data set. So make it, say for example 10 times, 15 times, and then obviously considering central limit theorem to be true, law of large numbers, you will basically have the values coming out to be normal. They come out to be normal, you can double check that. Now we basically took a set of observations. So what we do is that the whole data set we split into 1,000 each. Why 1,000? That was basically to check the distributions for all the parameters. So we took 1,000, found out the value of n, took another 1,000, found out the value of n. N is capital N, which we are talking about. That is the main thing which you want to find out. Again took another 1,000, found out the value of n. Now the question is that how many times? We took it 100 times. So basically 1,000 was repeated 100 times. So you will basically have 100 such n values. So taking that average of these capital N values in the long run would give us a decently good estimate about the value of D. D means the actual set of observation which you need. So once you find that, then you can basically proceed to the next step of trying to find out what are the estimates. That's one procedure. Another procedure can be you take the whole data set, take 1,000 of them, and at each step find out n. So find out capital N, estimate sigma hat. Again take another 1,000 n, estimate sigma hat. Continue doing in this way such that you will have different sigma hats. Find out the average of the sigma hat. That in the long run should give the value of your actual population. Now this I am telling the data set is quite clean. So you can use for a big regression models, this is a very good data set. The advantage of this data set is it has already all the parameter values already given to you for the population. So if you open the data set, I'll just double check the link, and I sent it. I completely forgot to add it here. So if you double check the data set, the population parameters are already given, like beta naught, beta 1, beta 2, beta 3 are already given. So if you do some testing on your end, your actual values based on which you want to compare are already given to you. Both the errors, standard errors, everything is given. So you need not worry about the background of the data. So based on that, we want to find out something. So what are those things from now? The results can be divided into two parts. One is the theoretical part which you want to study, and one is basically the practical part. So I'll just give what is of interest to us. Number one of interest to us is basically to find out the average sample size. Number two, I'll skip 2 and 3. I'll come to the fourth one. Second part is to estimate the actual parameters which I want to find out. Third value, so this was done for the 1000 sets. So I am now repeating it. When I repeat it, then what I need to find out is average of these averages, averages of these averages. Now I check two things. This is more interesting, while this may not be. See, remember one thing, when I am bounding the risk, that value is a theoretical, W is a theoretical value based on which you are trying to proceed. Now I want to find out that when I stop, the capital N value when I stop, that would also have a practical significance from the side of W, because when I stop, that N will be given. I plug that N and try to find out some practical value of risk. That means actually whether I am able to reach that value of the risk, yes or no. So I'll try to compare that risk value with the W value which I have based on which I am trying to proceed. That means I am going in a cyclic way, trying to basically consider W, find out the risk, and then again come back and compare with W. That's all, nothing else. So this is the risk value which I have, which I will do through the simulations, and I try to basically compare with my value of W. I'll skip this for the time being. Other value which was for interest to us is basically to find the CPU time. How many time? So CPU time is basically simply like this. Because if you are going to the market, doing a study and coming back, it takes time for you, both on the cost front as well as the time front. So it's an indirect method of trying to find out that whether we are exceeding the total time limit based on which we are trying to do our survey. It's just a very simple way of trying to find out that if it takes more time for the calculation, it means that you are spending too much time in your for your estimation problem. Now don't consider these type of CPU timings from the computational point of view. We are not checking the complexity of the problem. I'm just comparing my models with the existing one and trying to find out how good or bad it is with respect to the efficiency of the answer as well as the time it is going to take. So once you find out these, so these are some of the, okay, another obviously issue is for all the estimates I find out the standard errors also. So the dispersion, so if the standard errors are decreasing, it will give me that how robust my answer is. So now this we did not prove any theoretical results for the robustness, so I cannot comment anything about that. This is just a simulation concept which I am trying to use. So it can be used for prediction models, forecasting models, price prediction, number prediction for different types of goods which are sold. So these are, okay, I'll show you this and then start off a little bit about the optimization. So what I am doing is that I am theoretically taking these W values and then I am simulating 1000 100 times. So hence the double bars are there. So if I have the double bars, what I am considering is that my theoretical value of W is this, my actual value where I stop is this. So I should compare the first column and the fourth column. Similarly, if I want to compare these values, so if I want to compare the estimated value, this actual value is given, which I told is given the data set. This I am comparing with my actual value of theta which I am estimating. So if you find out, and this is the CPU timings which are given. So for different values of parameters, what are the parameters? One is lambda, one is W, one is A. A means overestimation, underestimation. You can compare different results. So they give decent results when your different loss functions are different, and they perform much better than the multiple linear regression. But obviously at the boundary conditions they would exactly match the multiple linear regression model, and they can be done in a simple optimization framework. I would not stop here. I'll just switch on the topic and go to some simple optimization problem, and then I take a break round about 3:15. Then Shankar takes over, and then I complete the optimization problem in the next one. So all these, just to mention, by today these 4 different sets of slides would be uploaded. Garud slides which I have just received yesterday night, that will be done, and other things which you can talk with Praveen about, the books and the photographs. Right. So this was just I wanted to mention as a. Now I'll just start with some simple reliability based simple optimization problem. So this is just the initial part will be the theoretical framework, then I'll solve a problem. Again, problem answers I can again hand over the codes. You have to run it yourself. Any nitty-gritties you need, I cannot solve it now. MATLAB codes you can convert in R, or you have MATLAB, you can most welcome to add it. So they are generally well commented. You can use them accordingly. So the first problem which I solved was basically for the regression, forecasting, and all this area. Next problem would be optimization from the finance point of view. I will just give the background and go into the problem. So in general, in optimization problem, our main task is to find out the best possible allocation of assets or some resources. So resources are some set of alternatives which you have, and you want to basically allocate your resources amongst the alternatives such that you are able to optimize some criteria. So optimization doesn't mean you want to maximize or minimize. It can be resources are constraints, you want to optimize and find out what is the total number of products you will produce, or it can be, say for example, how you will try to minimize your cost, or how you will try to find out how you maximize your gain. So all these things are there. So you want to find out a unique combination of the control and the decision variables subject to many constraints. Constraint can be, it can be 0, 1, that means you build the factory, don't build the factory. You transport the total number of goods from all the distributors, and you receive all the goods at the retailer's end. Or it can be your resource constraints are there for the products, resource constraints there are the number of actual products which you sell in the market, resource constraints can then be there for the raw materials, it can be there for the machines, it can be there for the manpower, all these things are there. So they are subject to some restrictions and constraints on the control of the decision variables in the domain space, and you want to basically optimize them. So your actual problem is like this. I am writing the general problem. So you want to optimize some multi-objective. If I capitalize 1, you have a single objective. If capitalize more than 1, is a multi-objective. So this optimization word is being used whether you maximize or minimize. It's in a very general sense. Now look at the first and the second constraint. So this PR means probability, but for the time being take out the probability. So if your constraints are greater than type, so obviously you would take out the probability, the beta also goes. So if you take out probability for the first one, beta goes. If you take out the second one, the beta goes. And you have the variables x in the n dimension, d is the m dimension, p is the l dimension. So these are like this. X is the decision variables, number of plants you want to bake, number of people you want to hire, number of products you want to make, raw materials you want to buy. D are the deterministic variables which are there, which are not under your control, but you know they are deterministic. And P are the number of variables which are not under your control, but they are probabilistic. Like say for example, I know that the prices are fluctuating, so obviously price would be a set of a parameter in the P scale. And if there are, I know my total production is fixed, so obviously it comes under the decision where the total D is fixed. And I am considering they are of different dimension, which is immaterial here. Now consider if betas are not there and probability is not there, you will have any different type of optimization problems are there. It is 0-1 programming is there, mixed integer linear programming is there, gradient descent, non-linear programming, linear programming, and all these things are problems are there, you can solve them. Now what happens if you have a probability constraints? So the first task for the probability constraint is to consider whether they are normal or not. So consider for the time being they are all normal. So if it is normal, so what you have? You have probability of such a random variable is greater than some fixed quantity with a certain level of probability. So what you do? You will convert them using the standard normal values in the standard normal tables, and they gets converted into capital Z and small z. So we can solve them. Now what if they are not there? So that is the main criteria or main crux of the idea we are trying to discuss. So we consider the class of probability both for the greater than type, equal to, and obviously you can have a less than type also, it doesn't matter. So you can have any one, all three, or a combination of three. So I am just taking them as greater than type, equal to type, and with probabilities of beta j, beta k. So beta j, beta k are of different values. So if the beta values are very high, that means I am more reliable on those constraints. So technically the beta value should be 1. So that means I am 100% reliable about those constraints. If the probabilities are less, so obviously the beta values will be less, and they can be modeled accordingly. Now I am trying to basically solve this problem using some concept of robust optimization, which I will discuss very briefly, and I will go into the reliability based optimization because I have one set of problems which had been solved, so I will be much more in a good state to basically solve this problem. So I will first discuss the reliability based concept, then I go to the robust optimization concept, and then solve and give our actual optimization problem from the finance perspective using the reliability based with data which is available either in Yahoo Finance or Google Finance and anywhere. You can get in from NSC, BSc, wherever. Now here actually what are the constraints which I mentioned is FIs are the objective function, in which case they may be linear or non-linear. So if the I is 1, it is single objective. If I is 2, is basically bi-objective, 3, more and more. So they can be linear, non-linear, combination of that, it doesn't matter. So I'll obviously you can either use some set rules or algorithms, or you can use heuristic methods. So heuristic method.
They are already, if you go to that previous slide, they are already greater than equal to, why we are adding equal to against Ck?
No, yeah, that's what I said. We need not add. Only one type of constraint is given, we can solve it. I am just writing it in order to make you understand. So if this is not there, you can solve it with the equality sign, or if the equality sign is not there, it greater than or less than type can be utilized. You are right. Now the probabilities are, there are capital J number of inequality constraints with a level of beta which is beta j, and beta j's can all be equal or not equal. There are equality constraints with the probabilities of beta k. So beta k is all equal, not equal, and then you have the vectors of probabilistic control decisions. Now they are probabilistic. Like say for example, if you design a car and you consider the decision variables to say, for example, be the material which you are going to use, then the material strength may not be known to you, so you consider that to be a probabilistic one. Another case can be where P will come for the design of the cars would be say for example maybe the wind speed, maybe the condition of the road, and say for example D can be you cannot increase the cost, you fix it at some level, so you will consider D set of variables accordingly. In say for example in finance it can be X can be the number of stocks you want to buy, which will fluctuate depending on the price. So price would be the set of variables which are under P. And what would be D? The total amount of money which you have. If I have 1 lakh rupees, I am not going to spend more than 1 lakh. So you will basically apportion your amount of money, the decision variables, and the set of variables which are not under your control, probabilistic and deterministic, accordingly. So if say for example the prices are fluctuating, the returns will also fluctuate. If returns are fluctuating, X, which is the variable for the financial optimization, are the returns of the stocks, so they will fluctuate. So obviously it will have an effect on your decision variables. Now similarly D is the deterministic control or decision variables which are not, we do not have any distribution, that they have fixed values, and P is the vector which basically has the probabilistic exogenous parameters of the system, and this B, J, C, K and all these things are the right hand side equality or inequality. So they can be 0 or non-zero, you can just convert them accordingly, so there is no issues. Now the non-deterministic nature of the optimization problem basically comes from, or the probabilistic comes from basically 3 parts. Consider it basically comes from 2 parts. One is X and one is P. Now when X and P are all normal, then combination of the normal distribution is always normal, and you can solve the problem very easily. What if they are not normal? So this I will try to give you a pictorial idea and then try to basically give you the reliability based optimization, how it can be used. It looks complicated, but it's not. So I should have basically made stage wise diagram, but it would. So consider the y-axis, the x-axis is there, and consider this dark green line and this dark green line only, there is nothing else there. So this dark green line onto the right and dark green line onto the left are the constraint boundaries, and I am considering a 2 variable problem only because it is easier for me to show. So if you see there is a red dot here, so if it is deterministic problem, so obviously considering the feasible set, the most optimum solution would be one of these boundary points. Consider this red point is the boundary point. So if it is deterministic, 2 constraint problem, the green one being the constraint where this is greater than beta naught, so that's why it's marked onto the dark green one, not on the dotted one, remember that. Here also it is dark green one, again it is deterministic one. So if you find out the best constraint, this is the red point, and you solve the problem. Now what happens if they are probabilistic? So consider if they are probabilistic, and consider for the time being they are normal. Even though I have not drawn it, I will try to basically make some sense of it. If it is normal, then actually, let me check whether I have this. So these are the boundaries, and you have the red dot is there here. So you basically have x1 here, x2 here, whatever the feasible region is, consider this is the optimal solution. Now consider they are non-deterministic and they are normal. So if they are normal, what you will have is, and consider that normal distribution is such that I am taking, say for example, 95% confidence. So these two dotted lines are these, this one and this one, or are those dotted ones which are green on the other side. So if they are normal, if I take a slice, so this would be the distribution which I will have with the mean value along the bold line, right? Any perturbations onto the right and the left would be given by this interval, right? Similarly, I will have, I am not going to draw it here for those dotted lines, this would be the normal case, right? Now consider two scenarios. Is the diagram clear?
Yes,
now consider both the variances are same. So if both the variances are same, and consider, and they are orthogonal to each other, so what would be the total combination of the distribution would be? One plane is coming from the right, one plane is coming from the orthogonal direction, both are circles. So as they merge, and the total coverage area would be a three-dimensional hillock. So if you take slices, it will be a circle because the variances in both the direction are same. Now I consider the variances are different, but they are orthogonal. The right hand side variance is more, left hand side is less. When they merge and they go, if you take the slices, they would look like a rugby ball. Ellipsoid, right? If you take slices, so either it is elongated along the x-axis or elongated along the y-axis, depending on which variance is more or less. Now consider the variances are same. When I merge them, they would be concentric circles. So the concentric circles would basically be the overall area, where the total area inside the concentric circle will depend on what is the probability. Larger or smaller the concentric circle area is, more or less the probabilities of the coverage. So consider this area inside is feasible. So obviously they are all feasible points. These are infeasible points. So actually this is the best solution if it is deterministic. If it is not deterministic, you will have such concentric circles where it will be tangent, and always the two lines which are the green and the yellow one would be tangent always, such that the loci of the point or the center of the concentric circles as they expand and contract would give you the trace of the best solution. See, you cannot go out of this area either onto the left or to the right. They are infeasible. If they are feasible, they have to be inside. And if they have to be inside, and if they are probabilistic, that circle would basically determine to what level the probability is. Larger and smaller the concentric circle is, more or less the probability or coverage is. So if I am looking at the midpoint, if it is both the variances are the same, the concentric circles which you are talking about, they would be moving as circles where the loci of the center would give you the best feasible solution depending on the level of probability.
Sir, can you repeat the part how that circle is defined?
Okay. See, consider this circle and this circle is tangent at this point, tangent at this point, it cannot go outside. Now consider if it is both are of the same variance, so some portion would be onto the left, which is inside these dotted lines, and some portion is onto the right on the dotted lines of this green. So these two coverage areas are feasible now, because anything outside is not permitted, because the probability is not met, because you have put a probability in the constraints, right? So anything outside here is infeasible, anything inside is feasible, but onto the feasible structure we are putting the constraint of the probability. So the area which is there, it will cover some area of the feasible set which is permitted by the probability. Larger and the smaller circles would basically be determined by the probability area, because if you see the normal distribution, and if you see from the top one dimension, more the probability is, more the coverage area it is. 95, 96, 99, 64 are smaller, so they are just concentric circles, right? So if it was one dimension, no problem, but it's two dimension, so obviously you have to find the best feasible point, which is the center, right? Now if it is normal, but obviously with two different variances, then it is basically a rugby ball. Now to take it one step forward, obviously there is no solution technique, you have just simulation techniques for that. Consider they are non-normal, not normal. So what type of distribution we will consider? I will consider different type of Gumbel distribution, extreme value distribution, generalized Pareto distributions for the case of the finance part. Like say for example, extreme value distributions can be considered for the flow of fluids in channels, or flow of fluids through rivers. So you can consider that. Or you want to do some tests for trying to find out that what is the geophysical characteristics as you go deeper into the ground. So you will use different type of non-normal distributions for that. Now if you consider those type of distributions, I have drawn it, I have used my best artistic skills, and you should appreciate that. So consider that I am looking, so technically they should be circles. Now they are not. Why? Because if I am looking from the top, and if this distribution is not normal, so this is a non-normal distribution. If I am looking from the right for other constraint, again this is a non-normal distribution. So if I project this, red one comes up and this is also coming to the right, I would get some value figures like this. So trying to find out the best solution is to find out the centroid, center of gravity. So how you find out the center of gravity? This would be some of the methodologies we will consider. So this, and okay, by the way, this work of reliability optimization comes more from engineering point of view. So they are used very heavily in mechanical engineering, heat flows, civil engineering for designs. So you can check this work. I think I have given the references. You can check. There are a lot of papers there here, but you won't find any book as such. All the papers are based on the simulation and all these things. By the way, these methods use different type of heuristics also if you do not get closed form solution. Because the reason is that when you break up this solution, which I will come down to later, you basically break down into two-step problem. One is to convert the probabilistic one into the deterministic one, and then solve the deterministic one using some optimization method. So if optimization method are not available, then you use the heuristic one, and then again come back to the solving the probabilistic one to the deterministic one. So it's basically loop-wise you go, where you have the conversion from the probabilistic to a deterministic one. This reliability based step will be used, and to solve the optimization problem from the deterministic to a better solution in the deterministic case, you will use like the linear programming can be used, non-linear programming can be used, all these methods which we all know can be used. But the next step where you add up and convert the probabilistic to the deterministic one is basically the essence which I am trying to discuss now. Now I have tried to put everything at one go, but that's why so that's why it took a little bit longer to explain, but it is it's doable. You only have to solve the algorithms. You don't have to basically by heart it. So these are, oh by the way, these are most probably, if I am not mistaken, in the MATLAB latest versions they may be available. I am not sure, but I have a feeling they may be available. If they are not, you can write the codes accordingly. Then so now what I was discussing about, if you remember the variances being different, so it's basically a rugby ball. So if you check the right one, which is the diagram C on the extreme right, there the region is circle. So as in the initial case you had the red lines which was A and B, hence the circle was more towards the center of the circle, wherever it is, the center of the circle was more towards the deterministic point. As you increase decrease the reliability, the line starts shifting more towards the feasible region. It cannot go out, it shifts more towards in. So obviously the reliability increases and the center changes. So these dotted lines I have just drawn hypothetically. So they are the loci of the point of the movement of the center of gravity of the circles. So if your variances are more or right, so they are all orthogonal. So in this case it is more on the one plane, less on the other plane. So I have tried to use some diagram and then try to basically explain these usages. So I will stop here and then you can take a break.